This is an overview of Austin and I's ML Agents Autonomous Car project. This video will be broken down into 3 parts: the background, an overview of our first attempt, and an overview of our second attempt, which actually worked. Over the course of this project and through broad experimentation, we developed a process that trained a model to drive a car while avoiding obstacles. We used the Unity ML Agents package, version 2.0.1, for this project. This package uses Python PyTorch library to train models, and we use the proximal policy optimization algorithm to train our agents, because it's more general and it's the default option in the ML Agents package. The quality of a machine learning model is dependent on the inputs that you give it and the rewards that you give it, so we focused on giving it the best of both. Also, to make the best model possible, we needed to only give it what it needed and nothing more. We noticed that the simpler our process was, the better our outputs were. The first step of attempt 1 was actually making the cars and the track. We used regular box colliders to make the track boundaries, and then we used rigid body 2Ds to make the cars. The cars moved forward and backwards with rb.addForce, and they turned with rb.addTorque. We gave these agents 4 observations. The first 3 were simple. The agent knew its position, the position of its target waypoint, and its speed. The last observation was a bit more complex. For this observation, we created a variable that tracked the angle between the last waypoint and the current target waypoint. This variable was created by putting the forward vector of both waypoints into the vector.angle function. The agent observed the difference between the angle of its forward vector and that variable, and then we normalized it by dividing it by 180, which was the maximum possible value. With the observations, the rewards and penalties were also very complicated. We penalized the agent every fixed update cycle to incentivize it to go forward. We penalized it for rotating too fast. We penalized it for hitting things, and we penalized it for going backwards. We rewarded the agent for reaching a certain speed and maintaining it. We rewarded it for approaching its target waypoint and for reaching its target waypoint. Largely because this approach was way too complicated, our results were pretty poor. The agent would just spin out of control most of the time and never really learned how to do anything. Also, because we were both inexperienced with making 2D cars, the movement in general wasn't optimal, so we ended up scrapping basically everything and restarting with our second attempt. Also reframed how we approached the problem and thought about the observations and rewards with the context of how we as people would think and approach driving without hitting things. In our second attempt, the agent was still given the raycast sensor so it knew where the walls were and what else was around it. We also let it know what its speed was and its angular velocity. It's very possible that the agent knowing its speed and angular velocity did not help it train at all. We gave the agent these specific observations because we figured that when driving, a human really only needs to know what's around it and where it's going to be, and that's where the speed and angular velocity observations came in. Because the second agent was supposed to just get the car to go around the track as fast as possible without hitting things, we only rewarded this car for not going backwards, for staying alive, and for going as fast as possible. We also created 2 custom raycasts that shot out to the left and right of the car on every fixed update cycle, and we rewarded the agent for maintaining a certain distance for those raycasts, which basically represented it staying a certain distance away from the wall, and we penalized it for being within that distance. At first, when we trained it, we had very interesting results. Because that threshold distance was kind of high, the agent learned that it wanted to reduce the large penalty that it would incur if it was within that threshold distance. So it didn't make turns. It learned how to go safely up and down the straightaways, but then it would get to a corner and it would decide that it wasn't worth it to make that turn. So it would turn around and it would just go back and forth on the straightaways. This isn't what we were looking for. It was massive progress compared to our previous attempts. So to fix it, we just lowered that threshold distance to be probably like a quarter of the distance. And when we trained that one, we were finally successful. Another interesting thing about this second agent was the training. So in the console, we could see the training progress and we could see the average reward and standard deviation. At some point, we noticed that the agent stopped getting rewards every 50,000 or so steps because it wasn't hitting anything and it wasn't dying. So it was just generating one huge, massive positive reward because it was doing everything right and it had learned very quickly not to hit anything and to go as fast as possible. Here's what our final output looked like. As you can see, the agent navigates the track without hitting anything. Another cool thing is it had just learned how to navigate the track without that being dependent on speed or turning. So after we had trained it, when we put it on inference mode and turned up the speed and maximum rotation, it was able to go around the track faster without us having to retrain it with different speed variables. Overall, this project was a success, and we learned a lot about machine learning, specifically that the inputs and rewards are the most important factors on whether or not your model is going to be successful. Thank you for watching.